The final subject in this appendix, 4412, is a little bit more advanced information. This is certainly above the introductory physics level, but it's useful information and it lets a person with more mathematical ability think on a higher level. And so even though you're not using it, it is a powerful methodology. I'm going to tell you a new way to talk about vectors that's even more advanced. We've talked about using vectors like x, just writing it this way, or as an arrow. We've talked about using a vector r as writing it as 3 times a vector, unit vector I plus 4 times a unit vector j. We've said, oh, we really don't have to use the I and the j. We can write r as a set of numbers, 3 and 4 and so forth. So it can be a set of numbers. And we could symbolically write this as something like xi, where we have x1, x2, and x3. That is the component form. Now I'm going to tell you about a slightly more sophisticated way of writing the vectors. I can write a vector and simply put a content inside, A, B, C, whatever this content might be, and put an arrow like this. And use this. This is the notation that's used that's very advanced. It can be used for quantum mechanics and algebraic studies that are much more advanced than we have here. And it turns out that every vector can have a dual vector. We write the dual vector in the opposite way. This is the vector that would be dual to this vector here. It turns out that a finite or infinite dimensional space is always going to be spanned by some kind of orthonormal set. And so we could write those vectors, we've written them previously, like we would write our unit vectors like I, J, and K, like this. But now we could write our unit vectors in a much more sophisticated way. We can write them as just I. And I has the property, and we can take a scalar product by multiplying a vector by another vector. So we could take the dual space I with another j, and this would be delta ij. That means the unit vector I times the unit vector I in the same direction is going to give a 1. But 1 times 2 is going to give 0 because they point in 2 different directions. These are the little unit vectors that point like this. Of course, the power in this is that I can not only use this with an I or a j, I can use this with a whole set of indices where they have a very complex range. And here I've given the scalar product as I and j is equal to this, or in metric space I can actually put a g as an operator in between the I and the j for that g that we previously talked about. Now the power goes a little bit further. I can use something called the decomposition of unity. The decomposition of unity is given by the sum over I of II, where I am saying that the space can be broken up into a set of unit vectors by projecting onto a unit vector and then taking that scalar product and pushing it into the ith direction. So for example, if I have a vector r in this new notation, I can say r is equal to 1 times r. Well, that's certainly true. Now this 1 I'm going to write as this, so this is equal to I summed over I times r, but this is the projection of r onto that unit vector. Well, the projection of r onto the x-axis is x, the y-axis is y, and the z-axis is z, or these three things are xi. So this is xi, I, summed over I. And these are the components of the vector in this basis. So we can say r is a vector, is given by this formula. We can likewise take a matrix, like a transformation, and put a 1 on both sides of it and expand it like this and end up with a sum over I and j of I, t, j, j. And now this becomes Tij summed over I and j. So that's a set of numbers times the vector action ij, which says project onto j the dual space and then project on the vector in the regular space times this set of numbers. And so this gives us a very powerful way of thinking about indexing over vectors, scalars, and so forth. We can then write abstract operations as x is equal to a linear transformation times y, and then we can put that in a given basis. And I'm not going to write that out again. Here I do it. I take the vector x, which is moved into in which I put a sum over I in between the L and the J, and you can see that it gives me an Lij times Y, which is the familiar form of that transformation. The final thing I want to mention is that I can have a linear vector space that's not a metric space, but instead it's a new type of thing called a Lie algebra. And a Lie algebra is very important in higher mathematics and higher physics, and it's defined by having a set of basis vectors, Li, and these objects are such that they do not commute in the regular sense. They're more like matrices. And so the commutator of two of these is always a combination of other ones in the space. So for a given I and j, this sums over k a set of numbers that are indexed by I and j. So for every I and j, there's a combination of vectors in the space. How is that different? Well, you recall that our metric space, when we had a product of two vectors, A and B, that this always gave a number, like 6. Here we're saying a new kind of product, A and B, always gives another vector in the space. This is antisymmetric also, so AB is equal to minus BA. And this new kind of product is called a commutator, and the Lie algebra is built on that commutator, and it can be used to build transformations in that space in a very interesting way by exponentiating. So we'll leave it at that, and that's kind of like a view of some higher mathematics, and I think it's always useful to look at higher mathematics as a kind of teasing process to say, well, this sounds interesting, I might like to know more.